Hello viewers, in the last program we had discussed the VI characteristic of a very important thyristor family member called silicon control rectifier SCR. Now in this program we are going to discuss the VI characteristic of another important thyristor family member called the DIAC. This is the experimental setup we have got. With the help of this experimental setup we are going to verify the VI characteristic of this particular DIAC, right? But before we take up the experiment, let me first explain a little bit of theory regarding DIAC. DIAC, as you all know, is a 4-layer semiconductor device and it is a thyristor. But if I compare it with silicon control rectifier, that is SCR, this is also a 4-layer semiconductor device. Now what is the difference between the two? The difference between the two from the construction point of view is that this silicon control rectifier, if you remember, had 3 terminals: the anode, the cathode and the gate. In case of DIAC you will have 2 terminals only, main terminal 1 and main terminal 2. So there are 2 terminals in case of DIAC, whereas there are 3 terminals, anode, cathode and gate, in case of silicon control rectifier. The 2 terminals in DIAC are main terminal 1 or MT1 and main terminal 2 or MT2. So the difference is that this terminal gate is missing in case of DIAC. Now what is this gate terminal? This is the control terminal of the device, and it is very clear from this description that the DIAC does not have the control terminal. So DIAC is just a triggering agent, whereas silicon control rectifier is a control agent. Okay? Now one more difference between the two is that this SCR is a unidirectional device, whereas this DIAC is a bidirectional device. Now let us understand what is the difference between SCR and DIAC. SCR, as I said, is a unidirectional device and it will conduct only when forward biased. It will not conduct when reverse biased. Whereas a DIAC, since it is a bidirectional device, it will conduct in both the directions, that is whether forward biased or reverse biased, the device is going to conduct. Now the constructional point of view, you find that there are only 2 terminals here, there are 3 terminals here, and from the performance point of view this is bidirectional and this is unidirectional. So this is the main difference between DIAC and SCR. Now the symbolic representation of an SCR, if you see, is like this. This is the symbolic representation of an SCR. This terminal is anode, this terminal is cathode and this is gate, whereas the DIAC is like this. You have 2 directional device and the terminals are like this. This is MT1, which is main terminal 1, and this is MT2, which is main terminal 2. Now look here, this is anode, this is cathode, this is gate, and the direction of flow of current will be from anode to cathode. So the arrow is put like this, whereas in this case there are 2 arrows, one is this, the other is this. So current can flow from here to here, it can also flow from here to here. So, main terminal 1 and main terminal 2 can be either positive or negative in positive half and negative half cycles. In positive half cycle this will be positive, this will be negative, in the other half cycle this will be positive, this will be negative. So, current can flow either from this to this terminal or from this to this terminal, whereas in SCR the current can only flow from anode to cathode when it is forward biased. So, this is symbolic representation. Now, let us see how the layer diagram looks like. Now, let us see how does the layer diagram of a diode looks like. There are layers like this. This is J1 junction, this is J2 junction, this is main terminal 1 MT1, this is main terminal 2, and the layers are P and P. Now, from this figure it seems that it is a 3 layer device, which is not true. We should have 4 layers. In fact, you have a small end layer here and also a small end layer here. Now, this and this small end layer, they form a big end layer. So, now you have 2 p layers and 2 n layers and becomes a PN type 4 layer semiconductor device. Okay. Now, let us see how does the VI characteristic of a diode look like. If I draw it like this, you will find that it goes like this, and suddenly at this point there is a shoot of current. Of course, this is voltage, this is current, and this is first quadrant characteristic. And at this point initially there is very small amount of current flow here from this point to this point, but at this point, which is known as VBO, of course plus VBO, breakover voltage, suddenly there is a shoot of current, that means there is an inrush of current, and we say that the device has triggered at this point and the conduction has taken place, the current starts flowing, but correspondingly the voltage at this point, say V dash, is very small. The current here is very high, but the voltage at this point is very small, say denoted by V dash. This is first quadrant characteristic of diode. Now, let us see the third quadrant characteristic. This is the third quadrant characteristic. Here also from this point to this point there is very small amount of current, and suddenly at this point, which is known as, of course, minus VBO, the current starts flowing heavily, and at this point you see the current is very high, but correspondingly the voltage here, say V double dash, is very small. Now, if I compare, if I see the characteristics, you find that both the first quadrant and the third quadrant characteristics, they look alike and they are absolutely same. Here I will repeat, initially there is a very small amount of current flowing from this point to this point, and this is known as leakage current. Leakage current. So, the leakage current is so small which does not allow the device to conduct, and at this point suddenly it starts conducting, it triggers, and the current goes very high, but correspondingly the voltage goes very low. And in the third quadrant also you will find that initially there was flow of leakage current only, and that current was not sufficient, the device did not conduct, but at this point correspondingly, which is known as VBO minus, the device started conducting, the current goes very high, but correspondingly the voltage, say V double dash, is very small. So, if I compare it with the characteristic of an SCR, the characteristic, if you remember, was like this. The first quadrant was like this, and the third quadrant was like this. This is third quadrant, this is first quadrant, and this is third quadrant. Okay? The characteristics were different, they were not alike here, but here you have both the characteristics are alike. That is why this particular device was only unidirectional. When it was forward biased, we say that it used to conduct, and it is known as a rectifier. Here both the halves, that is positive half cycle, negative half cycle, you see that this is conducting in the same fashion. So we can safely connect this device in an alternating current circuit, and it will conduct similar whether it is forward biased or reverse biased. So this is all about the VI characteristic of an SCR and the VI characteristic of a DIAC. We have compared them. Now in this program we are going to verify this particular characteristic, VI characteristic of a DIAC, with the help of this experimental setup which we have before you. In this experiment, this is the main board we have, in which I have rigged up a very simple circuit for verifying the VI characteristic of DIAC. This is the DIAC, you see, this is the DIAC, and VI characteristic of this device is going to be verified. Here is the load resistance here. It is a 100 ohm 5 watt resistor, and the load current will pass through this resistance, which will be measured by the help of an ammeter. This is the ammeter. This is actually an analog multimeter, but it is going to be used as an ammeter, and it will be connected between these two terminals. This is of course positive, this is negative, and it will show the current which is flowing through this resistor. Across these two terminals, you see, this is the positive, this is the negative, and a 0 to 35 volt supply is to be given, and this supply will be given with the help of this power supply, and 0 to 35 volts will be applied across these two terminals. Now there are two more terminals here, one this one, one this one. This is of course positive, this is negative, and across these two terminals this digital multimeter is to be connected in the fashion of a voltmeter. So this is all about the connection of this experiment, and now let me conduct the experiment for you. So first of all, I will connect the power supply, and the positive will be connected here at the red terminal. The negative, which is the blue one, will be connected at the black terminal. This voltmeter, the positive will be connected at this terminal. The negative, that is the blue one, will go at the black terminal, and this analog multimeter will be connected, the positive will go here, this is going to be connected as an ammeter of course, and the blue one, which is negative, will be connected across the black terminal. So what have I done? I will try to repeat. Number one, first of all, I have connected this power supply across these two terminals, which is a 0 to 35 volt supply. Across these two terminals I have connected this multimeter as ammeter, so it will show the value of current flowing through the device, and across these two terminals I have connected this digital multimeter as voltmeter, so this meter will show the voltage across this DIAC. So this is all about the connection. Now I will switch on my power supply. So the power supply is on, and let me put on this multimeter also. Adjust it here. So the experiment is now ready, the setup is ready, and let me start the experiment. What I am going to do is I will change the voltage from here, and look at this multimeter, which is an analog multimeter. Purposely I have used because it will show you a shoot at the time when the device is going to conduct. Let us see. I am going to increase this voltage. You see the voltage here is also changing. Voltage in this multimeter is also changing. I am changing this voltage. So far this has not conducted because this meter has not shown any shoot, and I have gone up to 30 volts. Yes, it is 30 volts. Now let me use this also. Yeah, here you see the shoot, the multimeter has shown the shoot. Let me use my specs also. And it has gone little out of range. So the value of the current is 0.3 ampere, 0.3 ampere. The value of the current is 0.3 ampere. The value of the voltage here is about 32 volts. And look here, the voltage here is 6.2. What does it mean? The VBO is 32 volts. The voltage dropped when this has conducted, that means voltage across the device after conduction is 6.2 volts, and the current is 0.3 ampere. I will write down the values for you. Voltage, that is VBO, 32 volts, current, which is the maximum value of current, is 0.3 amperes, and the voltage drop across the device is 6.2 volts. Okay. Now let me just put it off, and now I am going to check these points. If you concentrate on this, the characteristic I had told you, this point is of course 0, this is known to me. This point is VBO, which is 32 volt, known to me. This current is 0.3 amperes. I know this point, I know this point, I know this point. If I can get some of the points here on this, I can plot this characteristic. Okay. So now I will try to get some of these points before conduction of the device. Let us try. How can I get it? For that, I will change this multimeter into microampere range, because the current there is very, very small. So I put it in microampere range, and I will put the voltage in steps. I will increase the voltage in steps, and I will take down the readings correspondingly to this current, the voltage here, voltage and current. These two readings I am going to take. I will get about 2, 3 or 4 readings, and then I will plot the characteristic. Let us switch it on, and I am going to increase the voltage, and at that time, now it is in 50 microampere range. So again I use my specs. You see, the voltage here is 5 volts, and the current is, this is 50 of course, that means this is 4 microampere. Okay. 5 volt, 4 microamperes, 7 volts, it is 5 microamperes. I will write down 5 volts, and this is current. 5 volts was 4 microamperes, 7 was 5 microamperes, 10 is 20 microamperes, 15 volts is 25 microamperes, and so on. So I will write down these readings. I will write down the readings for you. Because this is voltage, this is current in microampere. When it was 5 volts, it was 4 microampere. For 7 volts, it was 5 microamperes. For 10 volts, it was 20 microamperes, and for 15 volts, it was 25 microamperes. These are some of the readings I have taken. And one more thing I have noted, VBO was equal to 32 volts. maximum current was equal to 0.3 amperes and the voltage drop, that is the voltage after the device conducted, that was equal to 6.2 volts. So with these ratings we can plot the whole characteristic. How do you plot it? You have 0, then you have 5, 7, 10, 15. You increase the voltage here, corresponding currents are there, so you get these points. Like that you can plot this characteristic. Of course VBO is 32 volts, you can get this point, you know this point, and of course this point is also known to you. How? Because this current is I max is 0.3 amperes. So this point is known to you, and corresponding voltage, which is V dash, was equal to 6.2. So V dash is 6.2 volts and corresponding current is 0.3 amperes, and this point, which is VBO, is 32 volts, and these points are also known to you, so you can plot this characteristic. So this is about the first quadrant characteristic. Now for the third quadrant characteristic, what do you think? What should I do? I think you guess it. You can guess it, of course. Here you have minus voltage and minus current. So what we are going to do here is we will change the polarities of these power supplies here and also the terminals polarities of the ammeter. So we will change this positive and negative polarities. The negative will now go here, the positive will go here. Of course you can let it be like that, and here also we will interchange the terminals. This will go here and this will go here. Again we are going to repeat the experiment as I did it for the opposite polarities. Now what will happen? You will get the reverse polarity characteristic. So let us put on the supply, and again you look at this multimeter, which will show you the kick. Of course we have to change its range to the multimeter, the original, that is milliampere range, 100 milliamperes range. Now I am going to again increase the voltage. Here, look here, this multimeter has shown a shoot, and that shows that this has conducted in reverse polarity also. Now I can repeat the experiment as I did for the forward biased, that is the polarities being in the other fashion, and I got these points. Here also you can get these points over here, 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 here. So you can plot this characteristic also. The VBO is known to you, the maximum value of current is known to you, and these points will be known to you, so you can plot this characteristic also. In nutshell we can say that we have plotted the first quadrant characteristic as well as the third quadrant characteristic, and that way you can verify that the VI characteristic of a diag will be alike, they will look same in the first quadrant as well as in the third quadrant. Now friends, what we have seen in this experiment, I would like to sum it up. The things what we have verified is that diag is a bidirectional device, unlike the silicon controlled rectifier. Silicon controlled rectifier was a unidirectional device and diag is a bidirectional device. That is why we could trace both the characteristics, that is first quadrant as well as the third quadrant, and we saw that both the characteristics were alike. One thing was very clear here. Second thing, we could know what is the value of VBO. For a particular diag, what we used here was dB3. Let us see, it is dB3. This particular diag, what we have used here as experimental diag, it is dB3, and for this particular diag we have verified that the VBO was around 32 volts. So these are the two very important points. The diag is a bidirectional device and we know its VBO also, and correspondingly we have seen the voltage drop when the diag started conducting, correspondingly the voltage drop was very less across the diag and the current shoot was very high. The maximum current what we got in this case was 0.3 amperes. So like that we have verified the VI characteristic of a diag. In the next program, we are going to see the VI characteristic of another very important thyristor family member, which is triag. Goodbye.